Okay, so here is the difference circuit where we have our various resistors set up in a way that results in the output signal being completely negated. So here in this upper right corner we have the follower circuit where the R2 is shorted and R1 is infinity. And so that results in, as you can see here, the output signal lagging behind the input signal. Okay, so here in the upper left corner is our inverting circuit, and we have chosen the resistor values to be such that the gain is 12. So we have a 12 kilo ohm resistor and a 1 kilo ohm resistor hooked up as in this diagram here. That results in an output that looks like this. So the output is significantly higher than the input, and it's inverted, so the valleys correspond to the peaks, and the peaks correspond to the valleys. Here's the differential amplifier output, where the blue is the output signal and the yellow is the input circuit. You can see that the blue signal is very noisy, but we took the average of 20 samples, and that made it less noisy. And then we took measurements at the high points of each of the signals, which allowed us to again calculate the slew and also the common mode gain by taking the peak-to-peak voltage. Yeah, so we measured the peak-to-peak voltage of channel 2 and channel 1, and then divided the channel 2 peak-to-peak voltage by the peak-to-peak amplitude of the input square wave on channel 1. And that allowed us to get the common mode gain. Okay, so here is the inverter graph that allows you to see with the red lines here that are the cursors how we measured slew rate, which you can see you have the change in voltage here and the change in time here, and so from that you can calculate the change in voltage over the change in time, which is also calculated here. And you can do that for channel 1. This is for channel 2, and then for channel 1 you can do the exact same thing. So our results then, shown in our lab assignment, got that the slew rate was 0.366 volts per microsecond, which is pretty close to the specified value is of 0.4 volts per microsecond, and it's 91.5% of the specified value, which makes sense because our resistor values were also very similar to the measured value. It makes sense that the measured slew rate would be very close to the theoretical slew rate.